We can probably begin. Welcome, everybody. It's a pleasure to welcome Pierre Raphael, who will be doing Minerva Mini-Course, starting with this lecture. This lecture and the next will be at this time in this room. And then I think the remaining lecture series is at the time to be determined. We'll receive an announcement. So anyway, without further ado, Pierre Raphael from the University of Cambridge, who will speak on singularity formation for nonlinear evolution equations.
Thank you very much, Max. Let me start with saying, really, the simplest possible words, how a pleasure it is for me to be here in Princeton. I feel extremely impressed by the hospitality of the department. I'm very honored to be welcomed the way I'm being welcomed. So it's really it's a great pleasure. So the second thing I'd like to say is that I've been under the mission of doing at least 2 elementary lectures to begin with. So I'm supposed to start at the elementary level. So what I would like to do today is really maybe I can make a brief plan of what I want to talk about. I want to tell you about singularity formation and about the vision that starts emerging on at least some aspect of these kind of problems. And really, so what I want to do today is really put in perspective a certain number of very classical results, in particular by emphasizing my favorite model, which is the nonlinear Schrodinger equation. We call you the basic facts here, and this is really an introduction to the subject. And then maybe in lecture 2, I'll tell you something maybe which is slightly less fun. I'll tell you about group of the critical norm, and which is in some sense for me, it's related to what can we say in general. What can we say in general on singularity formation? What do we know how to do? And in fact, there are very few things that are known in general, but there are a number of ideas here on energy concentration and nuclear theory, which I think are interesting to look at, which are propagated to various other different problems. And then really in lecture 3 and lecture 4, I want to tell you about what we really do in singularity formation. So I really want to tell you about what kind of groups do we know, what kind of singularities do we know, and how we study them, and put in perspective some tools, in particular to address the stability, which is something absolutely essential. So maybe today we really do some basic stuff, just to put the problem in perspective, explain what I'm interested in. Next time I'll tell you about really something, one aspect of the problem which has the advantage of being quite general, and which will be a way to really enter this kind of problem in full generality. And then I'll take the time to explain that essentially all kinds of singularities we know, they all fit in a certain class. It could be classified in some sense, and maybe what I'll do here, I'll show some details. I want to show some details on what's going on, and I'll mention open problems, because this is, there are many such problems. My advisor, Frank Merck, told me a long time ago, if you want people to get interested in what you do, don't finish the problem. Just start them and leave tons of interesting things to do. I hope we did that. We left absolutely tons of really interesting things to do, and we left them not because we don't like them, we left them either because we could not do them, or because, there are many things you can ask, many very, very interesting things that need to be understood.
There is a commandment in the Bible that says that we should always leave at the end of the field, we should leave it to people. Poor people.
I'm not sure this is where Frank learned this one, but maybe. But I totally agree. It's a very wise thing to do. Let people in and leave as much space as you can, so that actually. And this interesting thing is what you need. Okay, so let me stress again. So today I'm really doing something very elementary. So let me just tell you what I'm interested in, or what we're interested in. What's the singularity formation problem? How do I understand? What do we want to do? So of course, if you want to talk about singularity formation for nonlinear PDEs, there is a very famous problem, of course, which is the Navier-Stokes problem. And just to make sure, let me just, I'm not really going to touch much about it, but just to remind myself what this is. So typically I take x in R, I take the function u, the vector, t time. And typically, so the incompressible problem would be something like I have an evolution equation. So my fluid is moving with a type motion, and I have maybe some dissipation in the class. And I'm imposing compressibility on my fluid, and of course, I have some data at times. Okay. So this is typically the motion of the incompressible fluid. So I just remind you that that guard operator, with that guard of the function f, it's just the sum of g1 from 1 to b of b shades g. Okay, so I do this. So this is a vectorial equation. And you have pressure in the problem, but because pressure can be computed, it's really the nonlinear term if you want. So of course, this is also nonlinear because there's pressure here. So pressure is not it can be computed from the flow if you have a solution. Pressure should be thought as a non-local operator on velocity. So what's the problem? So the typical problem, and the problem was set up, if you want, by Laura a long time ago in the 30s. Essentially, what Laura understood is that you can set up the problem, you can solve this thing as an ODE in a Banach space. Right, so you will typically have local in time existence of solution. And the question you ask is, do we have global existence? Right? So, and what is the long-time asymptotic? Well, if the solution is so either lifetime is finite, and then we need to understand why, or the lifetime is infinite, and then we need to understand what the long-time asymptotic is. Okay, and this program, of course, which is a very general program, essentially he laid the foundations to understand the T in 2D. And in 2D, the answer that has emerged after this works in the 50s is very clear, is that in a suitable function space, which is the canonical one, strong solutions are global, that is the natural one, strong solutions are global in time. And in fact, the attractor is the linear. And it's simply all solutions if you want to start from any data in 2D, this thing is the vector field is going to go to a zero. Okay, and the point I want to make is why could he do it? And if you look back at the proof, the key, there are several aspect to this proof, but the key identity is just it's a linear identity. It's the fact that you have when you compute the variation of mass, so if you compute the variation of the integral of dx z squared dx, you find something like minus the integral of the gradient in tx over rd. So in fact, this is a linear identity. It's because incompressibility makes the nonlinear term disappear. Maybe there is a mu here which corresponds to the viscosity. And the point is that in particular, so it's a monotonicity formula that tells you that you control, you have a priori control of the echelon. Okay, so this quantity is under control, whatever you do, as soon as you have local a solution, you control this a priori. Another thing is that in 2D, L2, so this is really the L2 norm, like this. L2 square, and but in 2D, this norm is very special. L2 is very special. L2 is special because L2 it's a critical norm. Right, so critical with respect to what? So the criticality is respect, it's the way to measure, it's measured with respect to the scaling values of the problem. Okay, so criticality is with respect to the scaling values of the problem. So in this case, it's very clear if u of t and x is the solution of my PDE, then I can make another one by doing this, 1 over lambda u of t over lambda squared x over lambda. This thing is again going to be a solution, and if I call this guy, let me call it u lambda of t then the L2 norm of u lambda u2 is equal for all time to the L2 norm, maybe at time 0 lambda squared x u2. Of course, and this is because this is L2 of R2. Okay, and why this is important simply means that the fact that this norm is invariant means that whatever estimate we want to do in some sense, it must respect the scaling of the equation, and what this thing is telling you is that this norm, in some sense, it's a strong norm because it's really, it's the critical norm, it's the norm that does not see the scaling of the equation, so in some sense, it's a strong norm. Okay, so it's not a proof that you can prove that, you have to work a bit to prove the rest theorem, this is for sure, but in 2D, you could get, he could lay the foundations to get a complete answer, which is exactly the one that we make. Of course, if you go to 3D, if you go to R3, if you go to dimension 3, scaling variance is the same. Scaling invariance is the same. But if you ask yourself, if you want to compute the critical regularity, you will ask yourself, which, so for example, so if I define, if I not my Sobolev norm HS dot, so it means that the HS dot on the Fourier side. So I'm always in RD, right? I'm always in the whole space. So this is just the integral over RD of C to the 2s u hat of C squared. So if you ask yourself, how do I, what's the sort of, so how do I compute the critical regularity? Well, I just say, so the scaling of the equation is the same. This does not depend on that. This is really just dependent on the fact that this thing is quadratic here. So u lambda is 1 over lambda u of t over lambda squared x over lambda. But if you ask yourself which Sobolev norm is left invariant, if you ask which Sobolev norm is left invariant by the scaling of the equation, so when is it that u lambda t h dot in space is equal to u at t over lambda squared h dot, then you will easily compute that as it were. Okay, so you need to control half a derivative. The problem that you have is that the only a priori bound that you have is at the level of L2, so you're missing half a derivative. So a priori bound is L2. So now L2 is 2. Okay, so this is what I call, this is typical, and this will happen in many of the problems that I will mention. So this is a typical supercritical situation. And roughly speaking, it simply means, so this is the supercritical situation, it simply means that the a priori bound that we have is too weak with respect to the scaling of the equation. So what it means is that you cannot, it's been tried in many various different ways, it's not easy, you cannot control the flow, it's very unclear how to control the flow globally in time, so it makes the question of singularity formation still complicated. So interestingly enough, and this will be relevant for what I'm going to discuss maybe when I will tell you about supercritical problem and defocusing and lens, what this tells you, interestingly enough, so in the 60s, people discovered that they are this is a remark. Of course, there are classes of data in our plane, and these are data with symmetries, with special symmetries. For which one can prove global existence and this image. Right, so this is the realm of canonical symmetry as well. And just need to ask yourself, why is it? What happens? What does it mean? What happens? Why is it that in this case people can do something? Why can we all of a sudden salvage beta? It still is a supercritical problem. Well, the answer is very easy. For this class of data, you see you have a system of equations, but for this specific class of data, this symmetry group is propagated by the flow, and you have a new, if you want, here, conservation law. Right? In fact, it's the swirl that's transported by the flow, so you get some new a priori estimate on your solution, and in many ways this converse ratio is supercritical. So again, you get something, you control something above, it locks the system, and you recover global existence. So in some sense, it's a supercritical problem, but if you add some structure to it, or if you look for specific classes of solutions, again, you recover something.
Actually, it becomes critical, right? It becomes critical.
Yes.
Dimension 2, say, Navier stocks will be critical relative to the sum.
Yeah.
Or what is it?
In R2.
Right.
But here, what really makes things, what really locks the system here, is the fact that there is something else. It's not a conservation law, it's the transport of vorticity. That's the key information that holds only
some monotonicity.
So it's like a maximal principle in some sense. So it's retransporting in this case, but this is exactly what's going on here. There is something, it's not a conservation law per se, it's not like there's a general law, but it's exactly what's going on. In the flow, there's a quantity that actually can be, again, a priori controlled from the data, and this quantity is so strong that indeed then you...
Yeah, no, I can discuss if it is zero, you get the exact conservation law in dimension 2.
Oh, yeah.
And otherwise you get the monotonicity.
So you should think that, so this is, I mean, so of course, for general in R3, the question of singularity formation is completely open. So we know many classes of solutions that could be, I mean, very nice things have been done around the understanding of global flows for incompressible problems. But the question is really this. You see, what's puzzling with this picture here is exactly this. Are we missing something more general? There's some hidden structure, more general structure that indeed could block the flow. And is this just a special case of something more general that would allow you to control your solutions and sort and in some sense prove global existence, or is it really the case that you can make solutions which behave in a completely different way, and which in particular could lead to singularity formation? So at this point it's still completely open, and even the viscous problem in 3D, the non-viscous problem, just the Burger's problem is.
So I would say that sort of the definition of criticality should be measured relative to the best norm you have, rather than just the.
So I had this discussion.
norms.
I had this discussion with Vega.
Okay.
And so this is complete nonsense because it totally depends on what you want to do, what kind of problems you want to address, and typically, for example, on the kind of problem that he was looking at in particularly these questions of corner formation, for Schrodinger map equations, binormal flow, and these kind of things, which is actually deeply to the equation. It's only formally my scaling is -1/2, but I don't have a problem at L2 because he was looking for space. In some sense, he was looking for the actions of different groups. So here I'm really looking at the action of the scaling group. He was looking at the action of the Galilean group. And of course, then it becomes a different one, right? It's a question. But however, the point I want to make is that the only point here I want to say is that it is, however, true that there is a change of nature in the problem when you control the critical norm and when you don't control it, right? Be it regarding the question of singularity formation, global description of the flow. It's also true. There is if I think of nonlinear Schrodinger equation, wave maps, and these kind of things, the criticality of the problem matters a lot. Whether you are at the critical range or not at the critical range, the expected description either of singularity formation or long-time asymptotics of the flow is very different. Right? It matters a lot. The control of the critical norm is something that dramatically changes the expectation, and in some cases it's a theorem.
Yeah, my only question is what is the critical norm, right? Because, for example, in two dimensions, the critical norm would be available of infinity.
I would say differently. I would say you typically have a conservation norm. Is it scaling variable? If yes, that's your critical norm.
That's exactly what I meant,
You see, because
So it should be measured relative to the best possible
a priori bound that you can have in your product. Yeah, I think this would exactly be the way I would fit it. Okay, so what I'm going to talk about. So I'm not going to talk about incompressible fluids. So I will tell you more later about compressible fluids. Nonlinear Schrodinger equation. And key equations. And what I want to emphasize, so in some sense these are really basic problems, so I'm going to introduce them in a minute, but the only point I want to make is that just by looking at these other examples, what you can see exactly something like this. That is, you can see that in this kind of problems, if you go to the simplest possible models, typically this, you get an intuition, you get a certain type of intuition, typically something going along the line that no singularity should form. But in fact, when you start making the problem more complicated, when you start allowing for systems, when you start allowing for more interactions, very surprising thing can happen. And this is exactly what's going to happen here in the realm of nonlinear Schrodinger equation. So in some sense, it tells you that whether or not a singularity formation or energy concentration can happen is a delicate one. Okay, so and let me also say that the question of singularity formation for incompressible fluid it's a beautiful problem. It's just a drop of water in the fluid world and in the study of nonlinear waves. I mean, there are so many fascinating problems that are proposed by this equation. The only thing that is a little bit striking here is the fact that, first of all, there are analogies with this problem which I'm going to discuss. And the second thing is that we really don't know whether we are completely missing the point of hidden nonlinear structures here, which essentially no one has seen yet, or whether really this is just a standard problem test. just going to go to 0 nicely, and we're just missing the point on what to do. So this is what's going on. Okay, so time is up. Okay, so let me just abandon this and let me go really to elementary things about the nonlinear Schrodinger equation. Which is going to be the toy model I'm going to play with, and which has the advantage of being a non-linear dispersive system, which makes, and all the words matter here, because dispersion, but also the fact that it's a system, and which in some sense, of course, it's a toy model. It's a toy model. So like every toy model, it has some interesting aspects because there are things you can put your hands on, but of course it's just a toy model. It's certainly not going. It's just it's simplified, and the simplification, of course, should always be remembered. So what are we talking about? So we're typically the linear Schrodinger equation would just be my standard something like this. So I dtu plus is equal to 0. I give myself the delta at time 0, which is u0. So I have time and space. So time is r, space is now u, and u is complex. Okay, so this is really a system, and the nonlinear problem I will mostly consider would simply be I'm adding the simplest possible nonlinear term, so I can put either plus or minus u modulus of u to the 1. So p is an integer, so p is exactly, p is just a number bigger than 1. If I have the sign plus, it's the focusing model, and the sign minus is the defocusing. Okay, so what do I want to learn? What do I want to learn about this equation? Well, so I want to understand cell, I want to understand strong solutions, and which will be local in time. And I want to understand whether singularities can form. If not, how? If yes, how? If they don't form, I want to understand if the lifetime is infinity. I want to describe long-time asymptotics. Okay, this is really this is sort of really the problem. So what do you need to know on the linear Schrodinger equation? So let me just say, it was just a word on the linear equation. So of course, if you have this explicitly because I'm in RD, if I give myself a data, I can exponentiate immediately by Schrodinger. So we have the solution is to reality Laplace remote. And of course, I can make sense of this on the Fourier side. I can completely understand what my solution looks like. Okay? The fact that I am in the whole space gives me access to a Fourier analysis in space, and I can solve this explicitly. So I have formulas. And these formulas will tell me that U is some awful convolution. Some convolution is S of T and X involved in the data for some explicit guy. I can look at this and I can show that, of course, you have global existence, solutions are global, and they decay to 0 as T goes to infinity. You will find this in any textbook. So, for what I'm going to talk about, I don't like to think, so of course, so all solutions are global, and the attractor is. And of course, as far as conservation law is concerned, because this is just an isometry on the Fourier side, Sobolev norms are all concerned. Also, norms are invariant. Okay, so for what I'm going to talk about, I don't like to think of the Schrodinger flow this way. I very much prefer to think of the Schrodinger flow on the space side. Right, so if you want to do this, there is a formula, so just, I always print it out just to have it right. Something like this. So, position. So I have the following thing. So if V of t and x solves linear Schrodinger, so there's U of t and x, which is 1 over 1 plus t x over 2 u of t over 1 plus t x over 1 plus t e to the x squared over 4 times 1 plus t. Okay, so this is an algebraic fact. It's referred to in the literature as the pseudo-conformal symmetry. And of course, you have exactly the analytic for the wave equation. And I don't like this formula because I don't understand anything to this formula. That's not the way I want to write it down. And again, this will matter for what I'm going to talk about next time. So this is not the way you should think of this formula. This formula is telling you the following thing. It's telling you that you can take u to be of the following form. So it's 1 over lambda of t to the g over 2, v of tau and y to the I v of tau over 4 evaluative tau and y. So this tau is t divided by 1 plus t. X, I'm sorry, y is x divided, y is x divided by lambda of t. The new time tau is exactly t over 1 plus t. And of course, lambda of t is 1 plus t. Okay, and b of tau, in this case, it grows. I suppose it should be something like that, if you do the match. Okay, so what is the point of this formula? This point of this formula is telling you the following thing. It's telling you what solution to linear Schrodinger flow look like as t goes to infinity. It's written on the board. Because you see, when t goes to infinity, this is the solution of the Schrodinger flow. So when t goes to infinity, my renormalized time goes to 1. Okay? So this is, so what does it mean? It means that this is this is this is, if you want, this is tau, this is y. This is a solution to a Schrodinger. So in fact, it simply means that this profile has a limit as tau goes to 1, which is just in fact computed. You just take, if you want, at time 0, you take the initial data, which is u naught e to the I x squared over 4. You let it evolve by the Schrodinger flow until the time equal 1. And it will produce the limit of this profile here as a function of tau and y as tau goes to 1. Okay, so it means that this is a profile. So what does it mean? It means that if I look at the solution to the linear Schrodinger flow as time goes to infinity, what do I see? I see something spreading. Okay, my wave packet is spreading because I have a dilation here. Y is x over lambda of t. Lambda of t is going to infinity. So I'm getting wider and wider. Okay, so if I time 0, if you want, if I time 0, if at time 0 my wave packet was looking, this is my data, I take nice Gaussian data, then for large time, for t very large, what do I look like? I spread, I have a spreading, right, which is measured exactly by this thing here, so it gives me this profile v of tau and y has a limit, I don't know, let's call it v star of y as tau goes to 1. Okay, and of course, I have this crazy oscillation here. I look like this, but then I have to think that I have this e to the I tau y squared term here. I have this crazy oscillation here because this is divergent. Okay? So it means that a linear flow, you see, usually in textbook they tell you that the Schrodinger equation has no finite speed of propagation, of course, because you can be compactly supported initially, and then immediately mass is everywhere. But however, the speed of dilution, if you want, is something very specific. It's given exactly by the T, right? And it's nothing which is, of course, very reminiscent from the way the equation. Okay? So this is exactly what linear solutions do. They take, I have a nice wave packet, and it gets diluted, in a very specific way. There is modular oscillation, there is a profile, and a universal speed of defocusing of my wave packet. Okay? So what I'm going to talk about is exactly the opposite phenomenon. I will show you that nonlinear waves can do exactly the opposite of that. Instead of leading to deconcentration, they can lead to concentration. And again, it comes with profiles, it comes with a blow-up speed, and it comes with the whole structure that you need to understand. But this is exactly, I exactly want to study the opposite of this phenomenon. I want to study the phenomenon of concentration. Okay, so this is the first thing. The second thing it tells you, of course, you see immediately that if you start thinking in terms of function space, and this has been studied extensively, of course, this formula tells you that there are many norms you can consider. Of course, Fourier analysis is a very powerful tool, but it's telling you what you should do if you want to study, at least it gives you ideas of things to do if you want to study. Okay, so now let me say a word very briefly, because I want things to be crystal clear here. So let me say a word just about the Cauchy. Okay, so I just want to solve. So now I look at the, of course, I look at the nonlinear problem. And I want to solve I dt plus I plus, and I can take this plus or minus u is equal to 1. I want to take a division that I take 0 to 0. And if you want a strong solution, we know that essentially what we need is to solve we need to do a discount in the DNA formula. Right, that is, we need to write u as the u to the IT plus u naught plus the integral. So there are signs there, but this is irrelevant, so I just want to do something with this. So I have e to the IT minus star plus of u to the okay, so this is an operator, and I need to find a fixed point. And this is exactly, I'm solving this as I has u. And I just need to do my Banach fixed point. In a suitable band. And of course, for LLS, I have a favorite. I have a favorite candidate for Banach space, which is simply bound to the discussion that we had on Navier-Stokes. Of course, it's related to conservation. Okay, so what conservation laws do I have for my equation? So remember that in the linear case, also both norms are conserved. In the nonlinear case, only so there are two essential conservation laws, which are conservation of mass. So among all these two norms, there is one that is still conserved, which is which is that the L2 norm of my solution for all time is equal to L. And there's another quantity which is conserved, which I will call the energy. So E of u is E naught, which is equal to E naught, where the energy function is nothing but E of u, and this is the kinetic energy, the integral of R d and if I did plus minus, I have minus plus 1 over t plus 1 into the RD of radius of the t plus 1. Okay? So this is my energy function. So if I have a minus, this is focusing, and plus is defocusing. Okay, so, and of course it matters a lot because it means that in the defocusing case you have an a priori bound on the directional energy. In the focusing case it's more tricky because this quantity does not need control any of the two. This could be conserved, but these two quantities may become one. Okay? There could be compensation between two dimensions. So however, as far as local sheet theory is concerned, so in particular in the defocusing case, I have an a priori bound on the energy, so I would like to be able to solve my equation to close my band at fixed point, right, in H1, right? So I would like to be able to close in H1. But you see immediately that there's a problem, right? Because if you just use stupidly, if you just want to put, so of course you can always get a net to estimate. Right? If you want to get a net to estimate here, the problem will ask you typically to have some a priori estimate on u to the or u to the p equal 2. So maybe in H1 you will be able to do that. You will be able to use your sublet. But then when you're going to take the gradient here, if you just use the stupid semi-group estimate that this is not it, but it's just the isolation rule, then what you will get, the system will ask you to control the gradient up essentially. And if the only a priori estimate that you have is u in H1, your sublet tells you that you're going to be fine in dimension 1, but it's going to be bad in dimension bigger than 2. There is no way you can control that. So this is a very famous problem, and this was, of course, you can always take more derivatives, but if you take more derivatives, then your lifetime is going to depend on the higher norm that you took, and you have no a priori control on this. So there is, of course, this is something that was sort of heart of the problem at the beginning of the 80s. This was beautifully solved by Ginevra and Melo using smoothing, space-time smoothing of the flow and the so-called Streckers estimate. So this is really that's the Ginevra and Melo theory. Ginevra and Melo around 93. Local one-positiveness in the energy space. It's telling you that so typically so t is bigger than 1, p is bigger than 1, and you need SC to be 3 less than 1, and I'm going to tell you the name of SC is. So SC is equals to 1, so this is the critical exponent. Maybe I should have computed that. Then what's the theorem? The theorem is that there exists a unique strong solution. There is a unique strong solution, typically U1, which is continuous in H1, and this is the key, and if lifetime is finite, then H1 minus closed. So in particular, so corollary, in the defocusing case, if I am defocusing and if SC is less than 1, then lifetime is positive. Okay, which is exactly, that's one of the first big success of this theory, is that you have global existence in the defocusing case when you are energy subcritical. So what is SC? SC is the scaling of the equation. I should say that. What is SC? SC is the scaling regularity. SC is the scaling regularity. So how do I compute that? Okay. So I just ask myself, okay, so what's the symmetry group of my flow? So it's very clear. So I have I dtu plus 1 plus u plus 1 minus 1 du to the 1 plus 0. Okay, so it's very clear. If you want to make another solution, you don't have a choice. If you dilate space by 1 over lambda, so if I put x over lambda, I have two derivatives here. I have one here, so I need to put t over lambda squared here. Okay, but then I have a nonlinear term, so if I want to accommodate for it, I need 1 over lambda to the alpha, and there is only, so what I mean, you need to understand this is fundamental. This is a linear guy. This is a linear number. It's just because I'm counting my derivative here. This is a nonlinear number, and if you do the algebra, you will compute that alpha is 2 over q. That's the only one that works. Okay? And then the critical norm is just the thing that you compute by doing what I said. You just ask yourself how many homogeneous derivatives measure in L2. It's just a choice, right? It's just a way to count. How many, so if I take u lambda, so this is t dot, and I hs dot this. How many, so this is sc, how many sc, so that this does not scale. And the answer is exactly that. There is mu sc, which is is this it's the other way around? It's the other 2 minus 2. Yeah, it's the other 2 minus 2. And of course, then so this thing here is exactly telling you that you need to be SC less than 1 is the energy circuit. Okay, so this is the Millennium theory. Okay, so now, so this would typically, so it's telling you that in the defocusing case, essentially, you always have globally existing. Of course, the picture in the focusing case, the picture is different. The main difference, of course, is that the energy now has a sign. So I have minus 0. Minus 1 over plus 1, integral of u to plus 1. Okay, so it's not because I control the energy and the L2 norm that I control the kinetic energy of my equation, but so if you want to ask yourself when is it, the question is when is it that if I control these two guys, actually I also control this guy. Of course, this is just a matter of subleft, right? So all you need to know, you just need to know your subleft. So you just need to ask yourself. So if I have u in L plus 1, I just want to bound this by u that you got, which is just minus s plus d over 2 over p plus 1. Okay, so it gives me the value of s. So s is d times I have 1/2 minus 1 over p plus 1. So this is d times p minus 1 plus p plus 1. And then I can interpolate my derivative, so it's telling me that u to the L p plus 1 is controlled by u over 2 to the sigma. Actually, so I just put it to this 1 minus s, but u over 2 to the s. I can put this to the power p plus 1. Then I have twice p plus 1, so which means that for any function, I have the equality that the energy function controls half. This is half the gradient. This is kinetic energy. This is kinetic energy squared minus universal constant. L2 norm to some power, 1 minus s times p plus 1 and times the echelon of the gradient itself to the power, which is exactly what's over there. So twice p plus 1. Twice, I'm sorry. There's an s missing. Twice s p dB plus 1. Twice s p plus 1. So the question you ask yourself is, so you know that this is under control. So your Cauchy solution, this is under control. This is conserved by the flow. And you ask yourself, does this imply that this is under control as well? And of course the answer is simply that it's going to be true as long as this coefficient is 3 less than 2. Okay, and if my algebra is right, this should tell me, so the fact that this coefficient is 3 less than 2, so this is equivalent to p is 3 less than 1 plus 4 d. This is equivalent to SC. Okay, so it simply means that in the focusing case, if this is my Sobolev ladder, so this is 0 here. So this is 0 here, so this is 1 here. What it's telling me is that here I have no resistance. Okay, and it fails exactly. This point is excluded. Okay, so it's this region of exponent that gives you global existence. So this is really just Cauchy theory, but of course in the energy space, coupled with conservation laws and Sobolev inequalities.
So for cubic, the dimension should be 4. For p, still the dimension should be 4.
I'm sorry, say that again. So P.
For cubic, the dimension should be 4. P is a little
No, wait a minute. When cubic it's 2. The critical.
Cubic is critical.
It's a cubic 2. It's a cubic. It's the mass critical. It's not the energy.
Why?
critical.
But why is my? Oh, I see. Just for the focus.
It's for the focusing case. It's mass critical. So for the defocusing case, right? So let me say these words again. So for the defocusing problem, you can go all the way to 1. There is no problem. Just the Jean-Poincaré law and conservation law tell you global existence. Okay, this is defocusing. In the focusing case, it's no longer true. It stops at 0. So Cauchy theory a priori in energy space just goes all the way to 1, right? But you need global existence. Okay. And in fact, in the endless case, and this is actually something spectacular. In the endless case, this is sharp. This numerology is sharp, and this is by no means something obvious. So, so in the focusing case, the statement SC negative implies T equals infinity. So why is it the case? Simply because so this is the so-called virial identity. I'm going to play this bound to virial identity monotonicity formulas. Monotonicity formulas, and which in fact this is actually quite spectacular. They give you for free 2 things. They give you singularity formation in some regime. That's in the focusing case. And in the defocusing case, for the same price, essentially, they give you stuff. That's in the defocusing case. There is a beautiful algebraic machinery which is giving you both answer, and of course what's in the back of this. This is something I'd like to recall you because we're gonna actually derive the new monotonicity formulas next time when we talk about the behavior of the critical norm. So I want to review this briefly because this is really the starting point of the intuition. And of course, what's behind this is really the action of the pseudo-conformal symmetry. And as we will see, all we will do essentially is write energy conservation after having applied the vector field that generates a symmetry. So this is really deeply connected, of course, to Sergio's vector field. It's exactly the same thing. Not for the wave equation, but for the energy. So all these things are different. So why is my criterion sharp? So why do I have, why is it that when SC is positive, I claim that this implies that there exists a data which should keep going. And let me say that it's very rare that we are actually able to say something like that. It doesn't happen that often. So what's the proof? The proof has nothing to do with analysis. The proof is algebra. And the way it goes is as follows. So I typically have my nonlinear Schrodinger equation. And of course, the proof goes back of what you know how to do for the heat equation. So really the idea is to derive a monotonicity formula, and the way it works is as follows. So the monotonicity formula is in two steps. So step one, you compute the variation of the momentum of the solution. So you compute ddt of imaginary x at bar, and you find that I think there's a half here. I'm sorry, this is not what I want. And you compute half ddt. You compute the variation of the variance of the solution. So you square u squared, tx, tx. And you find that it's equal to this whole thing. X that right u bar, tx. There is something like that. Okay? And then, well, so this is bad. So it's telling you that what you're looking for is some monotonicity. So of course this has a very nice sign, but this is awful. This is just, this is something you can compute if you want in phase modulus, but it doesn't use it. So what you do is you take another derivative in time. So if you want, this is the lemma. This is the lemma. And the lemma says that, so again, so ddt of x squared u squared tx dx is 4 imaginary, so there's a 4. It's 4 imaginary of x that goes down. So this is always over all dx, and this is dx, this is the and the second identity is that when I ddt this quantity, x that grad u bar, this is equal to grad u squared, and I have a term here of minus epsilon d over 2 minus d over p plus 1 times the integral over of values of p plus 1, and this epsilon, so it depends, so epsilon is plus 1 in the focusing case, and epsilon is minus 1 in the defocusing case. Okay, so in fact, in the focusing case, you can re-express this. Just to have a correct formula, so otherwise I'm going to make it. Okay, anyway, so it seems like that is not very, but it's okay. So what you can do is the following thing. So what you can do, so this is just algebra, and of course what's here, so let me say it like this. So what you can do now, so in the focusing case, what you can do is the following things. In the focusing case, what you can do is the following thing. Of course, energy is conserved. This is conserved. Okay, so what you can do is a trade. You can replace this. You can replace this quantity by energy, and then it will produce a certain number of time u to the p plus 1. Okay, so you do this algebra, and what you discover is the following. You discover that when you compute the second derivative of x squared u squared, you find exactly 16 times the energy minus a constant which depends on t and p times u mutual. And this constant is positive. C if D is P is positive, if and only if S is positive. S is bigger than S. Okay, where I do so S is bigger than S. This thing here is positive if and only if the critical exponent SC is positive. So this means that P is bigger or equal than S. Okay, so this is really a brute force, purely algebraic identity. I will show you next time that, of course, this is just, you understand, this is just the Moravec written in a way or another on my nonlinear Schrodinger equation. The basic multiplier gives you something like this. I will show you next time how to use more subtle multiplier, how to play with this identity to actually control your critical norm, and in fact the use of this multiplier and what you can do with this kind of things. There are many things that are still moving, very interesting things, moving on the kind of things that you can produce. Okay, so what's the conclusion of this? The conclusion is very clear. So it means that now I can simply prove the following, which is a very classical thing. So if SC is positive, or 0, that is, this means that P is large enough. If the energy of your data is strictly negative, then if you have in your hands a very nice, well-localized, smooth initial data, there is no way it can be formed. Okay. The singularity must form somewhere, simply because of this identity, simply because all you have to do is realize the following thing, the proof. As follows, you have to realize that this thing here is positive, so it's because the second derivative of this is below d squared of x squared u squared is below 16 times the energy, which means that if I draw this function just by integrating, if I draw this, so I have no idea what it looks like, but if this is time, if I draw integral of x by u squared, then of course, so I don't know, times 0 somewhere, but what I can do is I can draw the inverted parabola with this 16 e0, so I'm just going to integrate, so I'm going to have an inverted parabola, which corresponds to this e0 t squared here, and I know that I must be below it. Okay, so there's nothing I can do. At some point, this quantity has to vanish, but any decent Cauchy theory will tell you that this is not possible. So it means that essentially, I will never arrive here. Something bad must have happened before. Okay? So it tells you nothing about the nature of the singularity. It just tells you that there must be pressure of classical solution.
Why is it called a virial identity?
Well, because this is interesting actually. This is more when people do multi-particle Schrodinger equation, right, that they consider this kind of virial identity, this kind of multiplier and etc. Right? The way you should think of this. I'm sorry?
So the thing it comes from canonical systems.
Yes, exactly. Multi-particle and this kind of thing. So this is exactly where they do this kind of thing. You understand that, maybe I'm going to make this in a minute. You understand that when SC is 0, this guy is 0. Okay, so it means that this quantity can be computed. It's a function of t. Okay, so what's going on here? It's very clear. The fact that I can compute that it's conserved, is simply because I have applied a conservation to symmetry. So this is exactly what's going on here. If you write down, so I should have said that. So let me point. So maybe this is a remark, but this is an important remark. So when SC is 0, so it means that 2 over 2 minus 1 is equal to 0, 2. Something magic happens is that if so there are two things that happen is that I discover that d squared t squared of x squared u squared is equal to 16 times the energy, which means that, again, I can compute this quantity explicitly in time, I just integrate twice. And the reason for this, what's going on here, is because in this case, if you remember the linear pseudo-conformal symmetry, so 1 over, so I wrote it like this, so it's, okay, I can do that, so 1 plus t to the d over 2, d of t over 1 plus t, x over 1 plus t, so this will be to the I x squared over 4t plus c, it's 1 plus 6, right? Okay, so you remember this is a symmetry, so if this solution, so is this guy. So this is a symmetry of the linear equation. Okay? But of course, when so this guy, so essentially this transformation goes through the linear part of the equation. If I had a nonlinear term, well, this is just dilation and phase. So because of the structure of nonlinearity, the phase is going to go through as well. So the only question is dilation going to go through? And the only question you need to ask yourself is it that this exponent, is it the same? Because I dilated with the same factor here. So the only question you need to ask yourself is it that, when is it that p over 2 is 2 over 2 minus 1, which is of course p 1 plus 4 which is as simple. Okay, so this thing here, when I write down the fact that this quantity is exactly equal to this, an equivalent way of rewriting this is simply by writing down conservation of energy for this guy, and this will give you this. Okay? So this is just, if you want, this is really just pseudo-conformal symmetry acting. It's the group it's the group of this transformation acting on the set of okay, so you get for free, what you get for free is you get existence of, of obstructions. Right? And really the argument is it's complexity. So the fact that you can show singularity formation with this kind of argument, of course, this is not exceptional. Right? There are many problems for which you can do that. Of course, you can do that for the heat equation. You can reproduce the exact same kind of identities for the wave equation. More surprisingly, maybe, and this is something we'll talk about later. There are more complicated systems where you can still show this kind of thing. So this is typically the PhDs of Thomas Guys, which goes back to the 80s, where you can use exactly this kind of arguments to show a breakdown of classical solutions. Breakdown of classical solutions for compressible fluid. Okay, so this is really, I mean, I'll write down this equation later, so let me just mention it generally. And in fact, it can also be done, it's more complicated, but it can also be very nicely done for viscous compressible fluid. So in some regimes, it's always the same. So in some regimes of nonlinearity. But you should think that this kind of convexity argument, that is this idea that some monotonicity can be exhibited as some functional need to change sign, and this is a positive function need to become non-positive, is something that exists in the literature. It's been done in substantially more complicated cases, when particularly you don't have this structure of sign, etc. Sometimes it seems like there is no algebra, but in fact there is. You just need to work much more. There is a beautiful work by Franckner that goes back to 92, where he proves for Zakharov equation. And this is certainly not, it's not obvious. There's something very nice going on here, is that in some sense, You see, these arguments, this is pure algebra. It means that all you do is you watch at quantities and you pray that it's the right sign. Right? There is no dynamical input at all on, I control this norm, I control that, and there's nothing. You just stare at the algebra. What Frank did here is that he understood that sometimes the algebra is not there, but you can input with more information, a priori bounds, in particular now bounds and group speed and these kind of things. And this kind of information actually, when you run it back into the machinery, allows you to conclude again. But this is complicated. So
it's still a contradiction argument.
It still is a contradiction argument, yes. But it's telling you that maybe it's not because it's not obvious that it's not there. Right? I'm not aware of many arguments like this. Maybe this more recent works here on viscous compressible fluids is also going along this line. It's not trivial. I mean, you have to work to actually understand the impact of viscosity here. And you certainly cannot stare just at the algebra. You need to derive some a priori bounds which control a certain number of quantities. It's much more complicated, and then you can get what you. So this is what I'm saying. So in some sense, this kind of argument is not rare. It exists and has been applied in various different settings. However, it has two weaknesses. First of all, it's of course there are many problems where there is no such algebra, and sometimes people look for it for a long time. And, we don't know that there's something like this, but it's typically not known. But for me, for what I'm interested in, really the weakness in this is that there is no information. No information on the nature of the singularity. At least not just. But there is something very spectacular, and there's something spectacular. And that is something that goes way beyond this kind of identity. That's something that's actually leading our intuition on many of these problems. It's the following things: that non-positive energy implies singularity. So you have an open set in the energy space where you know that singularity forms. So maybe various kinds of singularities, maybe they look very differently, but at least it's an open set. You know that there is something generated. It's not, there really is, if you perturb data there, you should still see singularity from.
I should point out that there is another type of similar formation of singularity, if you want. External singularity, which is also an indirect contradiction.
So it's a trap surface field, right? It's the fact that if you enter a certain regime, right, you cannot. This is exactly this. This is exactly what's going on. And shock formation also, some things like this. If you enter a certain regime, then indeed you're trapped. You're not being able to get out of it, and you have a contract. Absolutely. But you have to reach a certain place first. And then exactly. And then but this is exactly this. But it's not. My point, however, on typically on MLF, and it could be true for wine, etc. This is really telling you nothing on the nature of the singularity. And in fact, on most of the problems that we know, you must understand that singularity happens before.
Of course.
It has nothing to do. It has nothing to do. This function plays absolutely no role. Okay. However, something so I don't. In some sense, there is no information on the nature of the singularity. However, and this is the point I will make next time. So this is a teaser. What I do claim is that there is much more to understand. There is much more to understand in general. Underlying this kind of identity, and what I mean by that is that there are two things that I have in the back of my mind. There are so-called unit type theorems that are for non-positive for solution. Is non-positive energy. When you see unit type theory, it means classification. There is some And this is something that I will make explicit next time. And of course, this whole business is nothing but some form of Moravec's estimate. And you can be much more clever. You can be much more clever in the choice of multiplier. And it's not so much the choice of multiplier. You need to understand what kind of estimate you're doing. And what's in the back of this is scaling blind a priori bounds. And they are the key to understand for this kind of problem, and I will discuss this next time. It's the key to understand problems of upper bound and lower rate. Upper bound of lower rate and lower bound. And exposure of the critical. Because in fact, you see, what we will see next time is that this thing is not a machine. This is not a machine. You see, you think you're staring, you see, you have d squared, dt squared, or x squared, u squared is equal to energy minus something. Right? So in fact, this is a machine, of course, to get space-time bound on the something, and to control this kind of term that is essentially to localize the mass. It's the difficulty of nonlinear Schrodinger equation is, mass is moving around. Of course, if it's linear, you have Fourier analysis to control it. But in the nonlinear setting, it's not clear. So what I claim is that in this identity, but what's hidden here is really the control of this quantity and how it evolves. And this is going to give us the key to understand how the singularity formation process, when it exists, must lead to infinity, to the explosion of the critical mass that is in fact some sort of infinite concentration of the critical mass. So we'll discuss this next. Okay, so let me maybe say a few things in the remaining time. Excellent. So let me just remind you of, just ask now the following question. So we know, so in the defocusing case, if this is my Sobolev feather, this is 1. So we know that if it's defocusing, I have global existence. And it's not true. So here there exists finite time. And here it's dispersive. Okay, and this is the function. Okay, so I'll just maybe let's take a few moments just to recall you. So what can we say? So global existence is good, but what can we say? I want the long time description of the flow when t is positive. Okay, so of course in the defocusing case, so this has been extensively studied. There is an immense literature in the defocusing case on this problem, and the basic intuition is that unless your nonlinearity is really too, p is too small, the basic intuition is that indeed you have scattering. That is, you have t equal plus infinity, and linear flow is there. And of course, this is something which is completely trivial to prove if you allow yourself to have very simple, smooth data, and very nicely decaying data. So I suppose from here. Yeah. So this is something. So typically, for example. So maybe it's scattering, and if you want to prove scattering from A to Z, it's a little bit too complicated. Let me just remind you how you prove it. Right, so typically I'm going to give myself, a data which is very nice, well localized. And to make my life easy, I'm going to assume that SC is between 0 and 1. So which means that, then all the identity, and then I can prove decay just by doing exactly what I say. There is some sort of a vector field method. So how does this field go? So you typically introduce a function which is based on for transformation. So you look at this one. XU plus IT squared. So you understand, of course, this is the generator. We're taking the gradient of e to the IT squared before. Matter, right? We're taking the gradient in x of this. So it's the generator ENT. Then you look at this plus 8 t squared plus 1 integral of the RD of u plus 6. Okay? So this is a quantity, and of course because I have the very identity, and as I know, you see if I develop the square here, I'm going to get two types of terms. I'm going to get terms like x squared u squared, and I'm going to get terms like imaginary x squared u, which are nothing but my cross term here when I develop this square u squared. Okay, and in fact, so I can rewrite if you want. I can rewrite, so I can expand this. So I can expand this as being the integral of x squared u squared minus 40 imaginary of x squared u bar plus 8t squared. And there is a magic here, is that what's left is t squared grad u squared. So I have 4, I have 8, so I divide by 2, so this is 8 times 8t squared, and the functional that I see, so I get 8t squared is exactly the energy of u, but the energy is conserved, and this is exactly the energy of that. Okay, my numerology is cooked up to see exactly. Okay, so now I can compute, if I compute the variation of this function in time, I get exactly using my variable identity, so I know how to compute the derivative of that, I know how to compute the derivative of that, I just use my formula, and I get the monotonicity formula, minus 40 over p plus 1, I get d times p minus 1 minus 4, the integral of u plus 1. Okay, so this thing is non-positive. This is because I assume that this is positive. Okay, so I have a beautiful Lyapunov functional, and in fact, this functional now I just need to realize that this is something very special. Of course, this is the energy of someone. So now I let v of t and x to be e to the minus I x squared over 40 times u of t x, and I realize that f of t is going to be nothing but 8t squared times the energy of v. Okay, so again, the energy is the defocusing energy. The energy of v is half t squared plus 1. Okay, so of course this energy is not conserved. V is not a solution of the equation, but this is not what I care for. What I care for now, all I need to say is that 8t squared E of V, which is f of t, is less than f of 0. So I have an a priori bound on this thing, which is telling me that the energy of V is decaying, is less than f of 0 by t squared. And of course, now if I control the energy of V, so it's telling me that the energy of V, of course the energy of V, because I'm defocusing, I control the internal with the rate of V, it's controlled by t squared. But of course now I can play with my sub F, right? And the point is that, of course, the L2 norm of V, is just the L2 norm of U, because V is just a face, so it's the L2 norm of U, so it's conserved. Okay, so this thing is typically going to give me control some decay of V, so L2 norm with decay. There's some power here, so somewhere is going to give me decay of V, but decay of V is exactly decay of V, because this is just a face. Right, so this is the machinery to get decay. Once you get decay, you refill it to the beast, and at the end of the day, you get your scattering. Now, this is a lot of work. The only point I want to stress here is that this kind of monotonicity formula, this kind of very identity, in particular in the defocusing setting, you are really the machine to produce decay. And once you have decay, you work more, and you can have a complete description of the form. Okay, so again, this has been done in very general and functional frameworks. I just wanted to stress here the simplest
So this works out up to critical case, up to the critical case.
And all this, all these steps.
But it works at the critical case, right? This kind of method.
But see, the point at the critical case is that this thing is not going to give you. You will never at the critical case.
You don't get decay. I mean, you don't get the.
You can't get it anyway. At the end of the day, the enemy at the critical case is concentration of the energy. Right? So when
But you get the result for small data, basically.
Oh, for small data, yes. But,
Right,
but really, at the critical case, the enemy. So control of norms is not good here, because even if all this, even if E is bounded, etc., it's concentration that is the end. So you need to put your hands.
But we are talking about the defocusing case.
Yes. No. But still, in the defocusing case, getting global existence.
Up to the critical. I'm asking whether this method will give you global existence function.
No. It will not give you global existence at the energy created. You need to put your hand on the screen. So let me make another teaser. You know very well that this is Borgar's result, right? Back in the paper 99.
The spherical symmetric
In the spherical case, in the Finnish case, it's the I team that did the non-spherical case, and the Grela case did something very nice. He compared it in H2.
That's for the way.
Dynamically, it seems Fabrice Marchand is going to give us the seminar. I think it's the end of October. I think it seems like you can prove that just by integration of that. From A to Z. And as you can do this, it's answering your question. You can do very clever models from A to Z in the radial case, and put your hands on the Strickart norms Fontrage and prove global existence in the defocusing. I want to see that. I think this is very interesting. This is telling you that indeed there is much more, and we're just getting started with all these models. There is really much more. And it's also connected to all this models interaction. Right?
So in particular, all this work of Terry-Tau, which is very complicated, can be avoided.
The Terry-Tau and the item thing is non-radial. So I think what Fabrice told me that this is radial so far.
Oh, so it's still radial.
It's still radial. But the idea of the interaction models, the idea that the idea of interaction model is the idea that the interplay between several multipliers and the counting of how the interactions talk to one another creates monotonicity formulas that are a priori bounds that were definitely not understood, not like this. So. So I think in some sense what.
Really fundamental.
I think it is. I think there is much more. This is
It never works for the wave equation.
I'm sorry.
I was never able to make it work for the wave equation.
What the energy difference?
The interactive model.
Ah, this are.
It worked somehow.
And I will show you next time how to play with models. So just in the radial case, just something elementary, and yet again. A priori bounds that tell you something else, and they will not tell you anything. This is the beauty here. Here you get a priori bounds and you get decay. But if you do this in the focusing case, if you do this in a clearer way, you can get either upper or lower bound on the floor, and typically information typically something telling you that if a singularity forms, the critical norm must blow up, which is sort of the first appearing information to enter a more sophisticated description of the flow. It's hidden there. Right? It still is in there. There's nothing more than playing with energy conservation and.
No, but my question, I mean, the question I ask is whether all these methods works also for in the critical case for small data. And I presume it does. Right?
But in the critical case for small data, you really just use triggers, right? What else is to be done? If it's small data,
you could in principle still use this method all the way up to the, for small data. I think it should work.
I think it should work. Yeah, I suppose so. I suppose so. But of course, it's going to be very lossy, right? Because of course, this thing, I just wanted to show something simple. It's very lossy. You need decay. You need so it's a whole world to make this thing work just in the United States or this kind of thing. You have to work, right? It's not nothing is perfect. Okay, so I should not erase that actually. So okay, so excellent. So I just have the time to tell you, and this will conclude my introduction. So of course, so in the defocusing case, so we have T is plus infinity, and we have that. Of course, the picture in the focusing case is very different because, of course, when SC is negative, you always have global existence. There exists finite time blow-up solution if you evolve, but in all these worlds, there exists. You should think that when T is plus infinity, I should say. So if I go to the focusing case, and I decide that say so SC is between each is negative, so when SC is 0, I know that T is plus infinity, so it's very easy to make solution that to construct solution that scatter. There exists scattering solution, but of course there also exist solutions that do not scatter at all. And of course, a typical example of this solution is solid. Right, so what's a soliton? So in this world here, so I am with the focusing LS. Equal to 0, then a soliton. So here it's because I am with S negative. A soliton would be a time periodic profile that is U of T of X of the form Q of X to X. Okay, which leads me to solution of this equation. So every time you can find a profile that satisfies this thing, right? So you want to solve this PDE, and of course you want to solve, and then you want to solve. And then you want to solve, of course you want Q, right, to satisfy, you typically want Q to be okay, so here I want to say something because it's going to be central when we talk about singularity formation. You know, this is just a stupid advert. This is just telling me I'm looking for specific kind of solutions. I'm looking for solutions which have a specific dependence in time, and I'm reduced to this sort of equation. So the first thing I should say is that I decided to be time periodic. Maybe I could have decided to be stationary. Maybe I could have decided to be looking for a traveling wave, etc. For example, the question of whether this is the right equation or this is the right equation really is not dictated by the scaling of the equation. Okay? So if SC is less than 1, that's the right guy. If SC is bigger or equal than 1, actually you will not find decent solution of this. You have to go to this equation. The soliton becomes a stationary equation. So just saying these words tells you that the understanding of the nature of your nonlinear elliptic problem here depends on the numerology, okay? Which is something. So, of course, the point is that here it's completely trivial. But I'll show you problems where it's much less trivial, right? And understanding the link between the numerology and the question of the existence of solution to your problem, it's not so easy.
So wait, so are you saying that in for the critical case, for the C equal 1?
Yeah. The solution is
you
the
don't have solutions.
No,
you don't have solutions.
not with the minus. They will not have the correct boundary at infinity. That's the right path. Okay? But you know, if you give so this is the first one. So this can be said very easily when I have this kind of ODE, and I'm going to use two. Sorry, there are many things that can be said for two reasons. You can reduce to an ODE if you stick to regular solutions, which of course makes life easier. And you can still stick with the PDE if you want to, but there's something very special here. There is a variation function. Right? And you should think, let me just say the following one. When I talk about singularity formation, I will look for ways that behave in a specific way. So it will be, concentration will be understood by making some sort of an ansatz of this type. So I'm going to look for specific solution with a specific shape. And what I'm going to end up with is typically this kind of PDE, but sometimes I can reduce it to an ODE, so that's good, but what I typically use is the variational control. Right? So there are many problems, which in some sense are many elementary, but we don't know whether these objects exist or not because we are far from this. And that is certainly one of the major difficulties of fluid design.
So you're far from what? Sorry.
We are far from the variational structure. There is no simple gradient structure in your equation which allows you to conclude that the kind of objects you're looking for exist or does not exist. You don't really know how to construct it. Right? If you think of incompressible fluid, anything you want to do is neither radial nor with a variational structure, or it's very specific. But there's really this intrinsic difficulty that, which is in many ways a nightmare. And all I'm saying is that, of course, the existence of solitons, something that's been still studied since the 80s, but really the fact that you have these two things here is essential to understand and get very simple answers.
So you are saying that in this case you have this, but in other
exactly, in case you have this, but what I'm saying is that typically when I'm going to talk about broad profile and self-similar solutions or more complicated Schrodinger structure, I typically don't have this. So I need to do things differently. Okay? I wish, but I don't. So this is the first. So of course solitons, solitonic solutions, this is something that's been extensively studied. There is a very famous theorem which complete proofs is being achieved in two steps. So this starts with the Gildas-Linear back in the 80s. And the classification of the ODE cells was completed by Kohn. So what Gildas-Linear is the following thing. If you have a solution to this nonlinear elliptic PDE, which is such that it's in the energy space and it's positive. Right? So if you solve this, so if you want H1 and you're positive, then up to translation, you are ready. You have radial symmetry. So that's the Gildas-Linear, and so it means that you reduce to the ODE problem, and the ODE problem is that there's a unique minimal solution, so it's the minimal soliton. So it's the unique radially symmetric. So it's the unique radially symmetric solution to this equation. So Q is typically referred to as a constant. Okay, and this is a theory that has nothing to do with with speed. So this is something that holds.
So it has relative to
energy.
You
need to be below the energy. Exactly. So you really need SC less than 1, otherwise it's a different story. Okay, so let me, when you talk, so it means that there are solitons and there are time periodic solutions. Let me say that of course, these guys are in the picture. Let me just say, just mention, because I think it's worth keeping this in mind. Let me make a remark. You know, how much do we know, for example, the typical equation that people like to study is the Q. Okay, how much do we know about all solutions to these equations? So of course, if you're positive, so I want finite energy. I want Q. Well, so of course, if it's positive, up to translation there is only one. But if you're not positive, for example, there are excited states, there are more guys. But there's a very nice paper. So here I'm going to forget part of these guys, but it's the group around Paccard, Wade, and Pinot. These people make something very nice, which in fact is very much connected also to things that we've been trying to do dynamically. They tell you the following thing: you say take Q star to be the ground state. Solidarity. So that's the very nice profile. So you should think this is a radially symmetric function. So if R is that is distance to the origin, it's a very nice function. It decays exponentially. It's C infinity. This is the nicest guy you can think of. Then of course, what you can do is that you could try to take this ground state Q, and you could try to do the following thing. So maybe I'm in R2, and what I'm going to try to do is I'm going to try to put this profile here at the point x1, and maybe I'm going to put another of this profile here. So I put it back here, put another back here, then maybe I'm going to put another back here. And I'm going to try to make this be a solution to the full equation. So of course it's not going to work because it's a nonlinear problem. So even though you decay exponentially, these guys still interact. Right? If I make a sum solution, it's not a solution. But what these people tell you, it's the following thing: is that if you choose in a clever way, there's a this is so. If you choose in a clever way the points here, in fact there is a dynamical system underlying the question of where you can put this point. Then in fact you can make these interactions be null, and you can actually construct a solution in which the leading order is this, and the correction will be under control and will decay. So, but the point is that this position needs to be clever, needs to be chosen in a very clever way. So first of all, I think you need more than 20 bubbles. And of course, if you need to put them in a spherical space square, this is typically what people call a crystal. Right? Is that you need to place the points at very specific locations so that the whole thing can be accounted for as being a solution to this equation. So the conclusion is what? We are very far from a classification of stationary solutions. So this is something that should be kept in mind, because when people typically on this kind of problem, tell you that they can classify a regime, that they can have a complete understanding of all solutions, this is absolutely remarkable, because even in the stationary setting, we can't. We're very far, even just for this, we're not able to describe all solutions. We're probably very, very far from it.
But this will be, of course, extremely unstable, so it's not clear how much they.
So,
but
stability, I don't think this is the way you should think about that. Maybe you can perturb the equation in such a way that this becomes the attractor. It depends what, maybe you can couple these things so that this becomes the nice guy. It's certainly finite dimensionally unstable. See, you don't expect the linearized operator to be monstrous then. You would expect a modulo finite number of eigenvalues. Maybe this is an attractor of the form. And in any case, if you think in any way of being able to classify all possible solutions to the time-dependent problem, these kind of monsters should be in the picture. Right? So
depends on how ambitious you are.
It depends how ambitious you are. But I think that it's good to know that we are very far from even the stationary problem. It's very far from being understood, even with the variational structure, even with with quite a bit of information, we are not able to construct. Very far from understanding classification of stationary solution. So let me conclude for today just by saying one last thing that we've already done, of course, again, something very classical. So last thing I want to say is that, of course, one corollary of all this is that when S is 0, it is when P1 plus 4D, there exists an explicit solution. All you have to do, so let me, and why? Simply because all you have to do, remember, so I told you that the pseudo-conformal symmetry, so I gave you the pseudo-conformal symmetry like this, e to the x squared over 14. But maybe I should have put minus for the same price. This is also true. It's just I'm just playing with my symmetry group. And of course, what happens here is the following thing. You see, so I claim that if you use a solution, this is also a solution. So of course, it's true at the linear level. Okay, so at the linear level, what's going on here? At time 0, my delta is nice, and something becomes singular at time 1.
So you have to put a Q there to have explicit, right?
No, but so my point is that when it's linear, you know, the only point I want to make is that when it's linear, when t goes to 1, this goes to infinity, but this goes to infinity as well, and so it's scatters, so nothing happens. There's no singularity. But of course, if I have a singularity that stays there forever, then this is going up, right? So all I need to do is put here indeed, I take u to the q, and this is a singular solution. Okay, and I know exactly how the singularity forms. So the important thing is the following thing. So I can rewrite this, and this is what I'm going to do starting next time. This guy, I can rewrite it in the following form. I can say this is 1 over number t to the 2, some profile p of y of tau and y. So tau is the renormalized time. So here it would be t divided by 1 minus t. Y is x over number t, and p, so if I feed with this, so maybe there's a place here, maybe there's a place, and p of tau y, in this case, is exactly q of y, e to the I b of tau y squared over 4, but there's a big change now, b of tau is 1 over tau. So this has a limit. Instead of oscillating forever, this has a limit. As tau goes to infinity, that is t goes to 1, I converge to the perfect cube. Okay? So what does it mean? It means that the singularity forms by concentrating the solitary wave profile. Right? So concentration, so singularity forms by concentrating the ground state profile, asymptotically, the ground state profile at speed. So what we call the speed is exactly this, lambda of tau, or so lambda of t if you want. In this case, lambda of t. Okay, so it's not by 1 minus t squared, it's not square root of 1 minus t, it's exactly 1 minus t. So this is typically the kind of scenario for singularity for a nation that we have. After renormalization, the picture in renormalization variable is that you relax to universal.
Wait, so I'm a little bit confused. So this would work for any exponent, I mean, for any supercritical.
I'm using the pseudo-conformal symmetry.
Oh, so that works only in the critical case.
Exactly. Okay, so what I'm going to show you. So now
it also works for any cube, right? So you can use
it works for any cube.
For any stationary solution,
you can use any, absolutely, you can use any stationary solution. And there are 2 points I want to say about this. This picture is both universal and completely false in general. Okay, it's universal because all the bubbles that we know how to form, all the singularity formation process that we know, in a way or another, are tied to a scenario which is more or less like this. That is, after renormalization, there is a profile. You converge asymptotically to something. The problem is, who is the profile and what's the renormalization? Okay? And this I will show you totally depends on the algebra of the problem, and actually it's very likely that we don't understand most of these scenarios. We just put our hands on a few of them, but in some sense that this philosophy is completely general, except that this exact formula is ridiculous, in particular the fact that the broad profile is exactly Q is very specific, because you're facing a very specific problem, and the fact that the broad profile is given to you, that you don't have to do the watched form is something very, very specific. Okay, so next time, what I will show you is what can we say in general on singularity formation, and 2 hours will be absolutely enough, and we'll talk more about this model thing. And then in the last 2 lectures, I will really take the time to describe examples, different examples, on this kind of singularity formation, and give you a detailed insight into the kind of mathematics that you need to do to actually show the existence of these objects and understand their stability. So, that's it.
Thanks a lot. Yeah.
Sorry for the basic introduction. This was
That's exactly
this was
It was exactly what was necessary. I have a small question. I mean, actually, not a question, a demand. So you say that the stationary solutions in this case are very hard to classify, which is just something in typical course, this would be the rigidity problem, which there is a very clear set of stationary solutions, just a chaos solution.
yeah.
So it's kind of interesting that in this case it's so difficult.
Being
Where the problem
exactly.
is much easier.
It's not rigid at all. Exactly. It's
And
very
the other one,
it's much
the
easier.
other
I totally agree.
is much more.
But there's much more gaps. This is exactly.
Yes. So somehow you mentioned.
Are there any questions?
Did you see the picture of
You said a few times that this is a toy model.
Yeah.
For what?
To understand, energy concentration mechanism, how we interact.
With equations.
Then what? Are you talking about physics?
Was.
Or are you talking about PDEs? What's your, PDEs, there are terms that fit
Okay.
into this kind of stationary solution, interactions of solution, energy concentration mechanism, this kind of business. It's everywhere. And if you talk about the physics, it depends in which direction you want to go. Certainly, cubic LLS in 2D, this is optical fibers, laser concentration, and etc. This is typically the toy model for the main concern, propagation of electromagnetic waves in Kerr medium. Okay, so of course, this is always the same discussion. You have this very nice book by Sulam and Sulam. They explain you exactly this. They really take the physics. They derive the model, and they derive this kind of Schrodinger model. So you need to understand that typically the LLS equation, it's something that's derived in some sort of small data limit. Right? Something needs to be small. It's an envelope wave equation, so something needs to be small. So you can think that it's ridiculous to talk, if you want to talk about the physics, it's ridiculous to talk about singularity formation in the sense that indeed it's for small data. It's not the point. The point is that it has nothing to do with singularity formation. It's as difficult to show that the solution goes from 10 to the minus 5 to 10 to the minus 2, that make it blow up. It's the same thing. You see the mechanism that leads to the fact that something concentrate is going to interact with maybe something that will stop the singularity formation, and what comes out of this kind of system. These are certainly questions that have been very much addressed, and you cannot understand this if you don't understand the part where the wave focuses. It's essential.
Yeah, sure. It's just that, so NLS is just the limit of various physical systems.
Absolutely, it does shows up absolutely, but as this limit, typically the range, when I play with dimension, well, I'm not aware of dimension large or these kind of things. This is typically not what you get. It's dimension 3 or cubic nonlinearities and this kind of thing. So what I mean by a toy model, typically it's the kind of model where you see this kind of supercritical structure. You see the fact that some wave interactions are not controlled by your conservation law. You see that there is some freedom in the system that is, it's not locked, right? And you try to understand this kind of interaction. It's in this sense that it's a total model. There is no physics of defocusing LLS in Martian dimension. Not that I'm aware of.
But yeah, to be fair, I mean, you would be able to rephrase the question as being indeed showing that with these model problems, the dynamics gets into a regime in which somehow the derivations of the equations doesn't make sense anymore. Right? I mean, so let's say you start with nonlinear Maxwell equations. This will come up as a limit.
But this is exactly what I was saying, Sergio. This is exactly what you will learn from A to Z in this book by Schrodinger. This is exactly what they're telling you. Of course, you are in the spot. I don't remember you are in the real. It's an envelope equation. Okay, so you make some assumption on your electromagnetic field. So you ignore some sort of. But what you want to see is your envelope grow. Right? You want to see that your envelope starts. And then exactly you want to see that you get out, and then you want to understand where it sends you. What I'm telling you is that understanding that, and this is
okay. You will not do that
if you don't understand the mechanism. I'm telling you, showing that the thing goes from 1 to 100 is that stuff as making go up. It's the same thing. There's no. There was a super shortcut.
Just simply that you rephrase the problem.
In some sense, this is connected to what I like to call continuation after the rod, or interaction to precisely interact with structure that will stop the singularity, and then something else kicks in. But you can't start this if you don't understand the singularity formation mechanism. That is okay. This is his show. You can't.
Okay.
Are there any other quick questions? So if not, let's thank Pierre.
Thank you.